What is the relationship between tension and wave speed?
Our research question was, how does the tension of a string affect the velocity of a wave? We hypothesized that as we increase the tension in the string, the wave speed would also increase.
For our method, we attached a pulley system to the end of a table using a clamp, and then we placed our string vibrator onto the table. We tied a knot through the string vibrator and then pulled the rest of the string through the pulley and made a loop at the other end of the string. We placed the string vibrator so that way between the knot right here and where it touches the pulley was exactly 76 centimeters long. For our procedure, we placed one of our varied weights into the loop and we set our frequency to be a specific frequency for that trial. Then we switched out the weights as the machine kept running and recorded our data.
Our results showed a positive nonlinear trend between tension and wave speed. As we increased the tension, the wave speed also increased, but did not increase by the same amount each time. Our one-way ANOVA gave us a p-value of 1.19 times 10 to the negative 12th power, which is much smaller than the significance level of 0.05, which indicates that the changes in wave speed were associated with changes in tension instead of random variation. We also found that the relationship appears to follow a square root relationship, which means the wave speed is proportional to the square root of the tension.
Scientific integrity, we included all of our data points, including our possible outlier data in the 200-gram trial. We used repeated trials and we attempted to keep the experiment as controlled as possible by not moving the apparatus, doing all of our trials in one day to try and make sure that everything was the same. According to Welsh's two-tailed t-test, comparing the 10-gram and the 200-gram trials, our P was less than 0.05, which means that the difference between the lowest and the highest tensions are statistically significant. We also reported what we actually saw instead of making up data to support our hypothesis.
One of the biggest difficulties we encountered was that the machine was only capable of producing frequencies on the magnitude of kilohertz instead of hertz, which limits how precisely we could control the frequency. For some trials, we had to fine-tune the frequency in order to produce a clear standing wave, even when we were trying to stay at a specific frequency, such as 28 kilohertz. The frequency could vary about half a kilohertz. Another challenge was identifying the standing waves themselves. We had to estimate wavelength through observation, which can lead to uncertainties. Because of this, we used repeated trials and statistical analysis. We performed a Welch's two-tailed t-test comparing the 10-gram trial to the 200-gram trial. This test produced a p-value of 0.002, which is below the significance level of 0.05. This indicates that there is a statistical significant difference between the lowest and highest tensions. So even though we had uncertainty in our measurements, the statistical tests support our conclusion that increasing tension significantly increases the wave speed.
Accomplishments. We are excited to be done with summer quarter and we are congratulating Stuart for graduating. And then for acknowledgements, we want to thank Dr. Gilbloff for advising us throughout the process.
And thank you for watching this
Yay!
video. Woo!